Hello everybody. These are going to be the notes for 5.2, which is also about exponential functions, but in particular it's about the exponential function e to the x. Okay, so first let me show you where the e button is on the calculator. You can find e. It's right above this ln button here. So if you press second and then ln, you see that the calculator will display e, and then it asks you for what exponent you want. So if we wanted to evaluate just e, we can do e to the 1. Okay, and it tells us that it's about 2.718. Okay, so e is about 2.718. This is an irrational number. It keeps going forever. Okay, this is what the calculator tells us. This e is actually calculated by taking the expression 1 plus 1 over n to the n. So this is where e comes from. Okay, and then what you do is you make n get larger and larger. So if you plug in like 1,000, 10,000, a million, and so on, as n gets really large, this actually becomes e, which is about 2.718. Okay, and you're going to see this come up more in calculus. You'll have a better way of doing the definition for it. We'll see it actually this year for us later when we start doing compound interest and exponential growth. Okay, so that's all you need to know for now, is that Euler's number, this is what e stands for. Okay, so Euler's number is about 2.718. You know where to find it on the calculator. And now there's going to be some things that you have to do this section. A couple of those would be to graph functions that are related to e to the x. And then we're going to talk about an interesting property related to what we did with average rate of change a while back. And so let's talk about graphing first. So let's just look at e to the x. Since we don't have a calculator, or I mean, we do, but you should know how to sketch these without a calculator. We know a couple of things now. One, from before, since there's no plus constant or plus 0, I mean, sorry, not plus 0, but since it is plus 0, we know that there's going to be a horizontal asymptote at y equals 0. And as far as finding some nice points to graph, we really only need 3. If you plug in negative 1, 0, and 1, here's how we can kind of figure it out. We know that e is almost 3. Okay? So when you do e to the minus 1, it's like doing 1 over almost 3, or 1 over 2.7 or so. E to the 0 is just going to be 1, and of course e to the 1 is about 2.7. So as far as graphing, these are really the only points you need. You go to negative 1, and 1 over 2.7 is about a third. It's close to it. 0, 1 is right here. And then if you go to 1, you get just e, which we saw is about 2.7. So we go almost all the way up to 3. And then there's your graph for e to the x. Okay, and if you guys can remember these basic 3 points here. At negative 1, we're really close to the x-axis. At 0, we're at 1, and then at 1, we're almost at 3. Then you can graph any variation of e to the x, and we'll go through a couple of examples of how to do that. Okay, but just like the other exponentials from last section, the domain for this function is negative infinity to infinity. The range, as you can see, is going to be from 0 to infinity, and we do have that same horizontal asymptote, unless, of course, this is moved down or if it's shifted up. Okay, so that's e to the x. And now if we have something like y equals e to the negative x plus 1, Okay, rather than plugging in points, if you have these kind of memorized, then what we can do is kind of what we did in chapter, I think it was 3, where we kind of list what transformations are going on. So if you remember correctly, a negative here inside of the function, inside of the x, that means we're going to have a reflection over the y-axis. And then at the very end, we're going to have a vertical shift up 1. Okay, so now, as far as graphing goes, I'd start with the same e to the x, which is our parent function, and just put those points on the graph. So, 0, 1, 1 is almost at 3, and at negative 1 we're almost at 0, or about 1/3. And now what we'll do is just follow these steps. So first we reflect these points over the y-axis. So now this goes over, here I'll do this in orange. This point goes over here. This, when you reflect over the y-axis, isn't going to go anywhere. It's just going to stay right where it is. This, when you reflect over the y-axis, is going to go over here. So now you still have that same asymptote, but now the graph is decreasing instead of increasing. And that's it. Okay, not so hard. And again, we're doing this without a calculator. You guys can see that these aren't too bad. Okay, let's do one more just to be real sure. Let's say we have y equals negative e to the x plus 5 minus 3. Okay, so to get this graph, we're going to take y equals e to the x, so we're going to use this, and we're going to apply all those rules that we learned in chapter 3. So to obtain the new graph, let's see, first we always move left to right, and we can see right here that we're going to move left 5. Any reflections come next, and since there's a negative in front of the function, we're going to reflect over the x-axis. And then the last thing we do is any shifts up or down, and we can see here that there's a shift down 3. Okay, so we're going to do the same thing we did with the other graph. Okay, so I'm going to start with the parent function, e to the x, 1, 2, 3, 4, 5, 6. Okay, so e to the x, again, is something like this. So here's the original. Alright, and now we're going to follow these steps. So we're going to take these points, move them all left 5. So this point goes left 1, 2, 3, 4, 5. This y-intercept gets shifted over 5 units. And then this point, which was almost at 3, gets shifted over. So we've done the first step. The next step is to reflect over x. So now these points just go over the x-axis. So here, here, and then this one will go almost to negative 3. And then now we're going to go down 3 units. Okay, so all these points are going to shift down. And a good guide is usually the horizontal asymptote. If you've noticed, we started with a horizontal at y equals 0. Moving it left 5 doesn't change that. Reflecting over x doesn't change the horizontal asymptote. In fact, you can see that it's still here when you plot these points and connect them. Now when we go down 3, 1, 2, 3, I'm going to actually go ahead and move my horizontal asymptote down 3 units first. And there's a couple ways that you can graph these points. You could literally just say, alright, I'm going to take this point and I'm going to go down 1, 2, 3, so almost to negative 4. Take this point, which was at 1, shift it down 3, so now we're going to go to negative 4. I guess I should have said this point was almost at 0, so now this will almost be at negative 3. That's a better way of thinking about it. And then this point, which was almost at negative 3, will be almost at negative 6. Okay, so the new graph is going to look something like this. Okay, so that's kind of how to graph these, move them around, shift them around. No big deal. The last thing I wanted to talk about in this section was actually about something that we've done a while back, but now we're going to deal with a little more, which is average rate of change. In particular, with e to the x. Okay, so again, if we draw a rough sketch of e to the x, we know it looks, something like that. And, let's say I wanted to find the average rate of change from 1 to 2. So from this point to this point, you guys remember that if you connect these 2 points, the average rate of change is going to be the slope from here to here. And the formula for calculating average rate of change was f of b minus f of a over b minus a. So if the interval that we're looking at is from 1 to 2, then our formula here is going to tell us that we can do f of b, which is f of 2, minus f of a, which is f of 1, over 2 minus 1. And now if we're using this function here, e to the x, that just means to do e squared minus e to the 1 over 1. This means you plug in 2 for the exponent, you plug in 1 for the exponent, and then 2 minus 1 is just 1. So this is our exact rate of change, e to the second minus e to the 1. If we go ahead and type that in the calculator, we get, let's see, e squared minus e to the 1. We see that the average rate of change is about 4.67. Okay? So that means that from here to here, the slope is about 4.67. Okay, so you guys know how to do average rate of change. You should be able to do that with e to the x. But also, you should be able to do something new. So let's take, again, that same, e to the x graph. So let's say this is e to the x. And let's say here we are at 1. Let's say I wanted to find, not an average, so I could go out to 2 and 3 and connect all these points and find these average slopes. Let's say I actually wanted to know the slope here. Okay, you might have learned in physics already that a good way to do that is to kind of draw a line that we say is tangent at this point. You'll obviously do this a lot more in calculus and have more precise ways of doing this. But if we find the slope of the tangent line slope is the instantaneous, this is what we call it, instantaneous rate of change. So it's not an average. It's the real rate of change that's happening at this value of x equals 1. Okay, and one way that we're going to do that, but obviously for this function there's going to be something pretty neat that happens. We're going to say, instead of finding an average like we did here from 1 to 2, let's get really close to this point. Okay? And the book does the same thing, but they actually take it step by step by step. I'm just going to do it right away and say, you know what? If I want to get really close here, I'm going to argue that the instantaneous rate of change will be very, very close. It will be approximately equal to the average rate of change from, let's say, 1 to 1.0000001. So what does that mean? If I'm looking back here, if I'm at 1, so let me see if I can zoom in. If I'm at 1, okay, and I go just a tiny little bit to the right, so I can even draw it because 1.0001, 1 point, how many zeros? 1, 2, 3, 4, 5 zeros. This point is practically right here, right on top of it. I mean, it's so close to it that you can't even tell. when I find the average rate of change between 1 to 1.000001, this average is going to be pretty much the same thing as this tangent line. Okay, so for instance, if I plot e to the 1, that's right here. If I plot e to the 1.5 zeros in 1, that's just going to be a new point that's pretty much right on top of this other point, so that when you connect these, you really do get something that's pretty much the tangent line. Okay, so what we're going to do is go ahead and do that calculation. Let me just zoom out, sorry. And to do that calculation, we'll do that same average rate of change formula. So f of 1.000001 minus f of 1 all over 1.00001 minus 1. So now it's e to the 1.00001 minus e to the 1 over 0.000001. Okay, obviously we're going to type this in the calculator to see what this looks like. Okay, so right now this is kind of all the legwork for what you guys really need to know. We're not going to do instantaneous rate of changes like this all the time, because there's going to be a nice, not really a coincidence, but a special property of the exponential function. So, okay, if I type this in, e to the 1.12345 zeros, and then 1 minus e to the 1. And I'm going to divide that by 0.000001. We see something that looks familiar. 2.7182. Well, that's actually e, or really close to it. Okay? So 2.718283 is what we're getting when we do this. This is almost e. Okay? In fact, that is the special relationship. So let me go back to this picture here. The special relationship for e to the x is that this is the only function in the entire universe where if you wanted to figure out a slope or an instantaneous rate of change, you don't have to do anything because the answer is whatever you get when you plug it in. In other words, the slope of the function is itself. Okay, and you'll see that in calculus and you'll prove why that is. But for instance here, we were at 1 and then e to the 1. So if I did all this approximation stuff, I got pretty much the same thing I would have gotten if I had just plugged in 1 into the function. Okay, so this leads us to this property, the instantaneous rate of change for the function e to the x at a point, let's say at x equals a, is exactly what you get when you plug it in. So e to the a. So this is what you need to know. You're not really going to have to do these calculations too much, but what you should know is that we got this pretty neat property here. So some quick examples to illustrate. If I said, find the instantaneous rate of change for f of x equals e to the x at the point x equals 2.5. Hopefully you kind of see what this means. This is telling us that I don't have to do any work. All I do is plug in 2.5 into x and I'm done. This is your instantaneous rate of change. This is your slope at the point x equals 2.5. It works for any point. So if I did it one more time, let's say at x equals 3,000, that'd be a really, really large slope, but it works the same. At 3,000, the slope or the instantaneous rate of change is going to be e to the 3,000. All right. Thanks for listening. See you guys tomorrow.